Imagine a massive, multi-million-dollar clinical trial. Like, researchers are testing this groundbreaking new painkiller.
Okay, setting the scene. I like it.
Right. So they ask thousands of patients to rate their pain on a standard scale from 1 to 5. The trial wraps up, the data gets fed into the computers, and the researchers calculate the mathematical average of all those pain scores.
Which sounds totally normal to most people.
Exactly. It sounds completely normal. They publish the results, totally unaware that their foundational statistical choice is, well, it's fundamentally mathematically flawed.
Yeah, and it's wild because that kind of clerical error, it happens far more often than people realize.
Really?
Oh, absolutely. In health research, treating a category like a hard mathematical number isn't just some, minor spreadsheet glitch. I mean, it can completely invalidate years of expensive work.
And that is exactly why we are diving into this today. If you're prepping for your exams, consider this deep dive your absolute definitive study session for Lecture 10.
Yes, the measurement of study variables.
Exactly. Our mission today is to make you absolutely exam ready by unpacking all the core multiple choice questions, the MCQs, from your source material.
But we are leaving rote memorization at the door.
Oh, 100%.
Because, memorizing bold text might get you through a pop quiz, but when the actual exam inevitably tweaks the phrasing,
Which they always do.
always.
Right.
When they do that, rote memorization just shatters. You really need to understand the underlying architecture of the data.
Right, because mastering how we measure and classify variables is basically the bedrock of all good research.
It really is. If you misunderstand the nature of a single variable, you'll end up applying the wrong statistical test, and like we said, your entire study falls apart.
So by the end of this conversation, you won't just know the bold-faced answers, you're going to actually see the mechanics of the statistics.
That's the goal.
So let's start with the foundation. Before we can even dream of analyzing a giant data set, we have to know what kind of data we're actually holding.
Right, which brings us to the types of variables. Broadly speaking, health data is split into two main camps.
Categorical variables, which group people, and numerical variables, which measure them.
Exactly. And within categorical variables, you have two subtypes, nominal and ordinal.
Okay, let's break those down.
Well, nominal variables are just names. They are literal buckets with absolutely no inherent hierarchy.
So think gender, place of residence, or eye color.
Right. There is no mathematical sense in which blue eyes are somehow greater than brown eyes.
Which directly addresses question 19 on your exam sheet. It explicitly asks which of the following is not a nominal variable.
And the options are gender, age, place of residence, and color of eyes.
So age is the odd one out here.
Precisely. Age is a measurement of time, so it's numerical. Gender, residence, and eye color are purely nominal buckets.
Okay, got it. So that's nominal. Then you have ordinal variables.
Right. So ordinal data still uses those categorical buckets, but there's a meaningful ranked order to them.
Hence the name. Ordinal. Order.
Exactly. One category represents more of something than another, but, and this is crucial, you don't know the exact mathematical distance between them.
Okay, let's look at question 1. It asks about patients categorized by blood pressure stages. So normal, pre-hypertension, stage 1, and stage 2.
And question 29 is really similar, asking about socioeconomic status, categorized as lower, lower middle, and upper.
For both of these, the answer is ordinal, because there's an obvious rank.
Right.
But wait, let me play devil's advocate here for a second.
Go for it.
With ordinal data, like pain scales say, that 1 to 10 scale we talked about earlier, doctors average those numbers constantly.
Yeah.
Right? They'll walk toward and say, oh, the average pain level today is a 4.5. Are you saying that's mathematically wrong?
Strictly speaking, yes, it is mathematically invalid.
Wait, really?
Yeah, think
Yeah.
about it.
Yeah.
The distance between a pain level of a 1 and a 2 might just be a slight annoyance to the patient.
Like a paper cut.
Right. But the distance between a 9 and a 10 could be agonizing, system-shocking agony. The intervals are just not equal.
Oh, wow. I never thought about it like that.
So when you calculate a mean, the math assumes every interval is identical, saying the average socioeconomic status is 2.5 or average pain is 4.5, imposes this rigid mathematical structure on categories that simply don't possess it.
That's fascinating. It's like a really common statistical sin.
It absolutely is.
That completely changes how you look at clinical charts. Okay, so that's categorical data. Let's shift to numerical variables, the actual hard numbers.
Right, the stuff you can do real math with. These split into continuous and discrete variables.
And continuous means the number can be measured infinitely precisely, right?
Exactly. So look at question 8. which asks about cholesterol levels, or question 15 asking about height in centimeters.
And there's question 25, too, asking you to evaluate the statement, height of students measured in centimeters is an example of a continuous variable.
And for all of those, the answer is continuous, because you aren't just exactly 150 centimeters tall.
Right. Depending on how precise your tape measure is, you could be 150.5 centimeters or 150.55 centimeters.
Exactly. The number flows continuously without breaks.
But then look at question 7. It states, number of children per household is an example of a continuous variable.
And the answer you need to mark for that is false.
Because, obviously, you cannot have 2.5 children.
Right. When you are counting distinct whole indivisible units, that is a discrete variable.
So in a clinical setting, that would be like counting hospital beds.
Or the number of asthma attacks a patient suffered this month. The data jumps from 1 to 2 to 3.
Yeah, there is no continuous flow between those whole numbers. You can't have a fraction of an asthma attack.
Exactly.
Man, designing a survey suddenly seems a lot more treacherous. Like, if you offer a continuous slider for a discrete event, you've basically ruined your own data.
You really have.
Okay, so we've identified our variables. The next logical step in any research study is to summarize that massive, messy pile of data into one single representative number.
Right, we need to find the middle.
In statistical terms, you are looking for the measures of central tendency. And the three main tools here are the mean, the median, and the mode.
Yep. And question 2 explicitly asks, what is the most commonly used measure of central tendency?
And the answer is the mean, just the classic mathematical average.
Exactly. And honestly, we probably don't need to labor over how to calculate a mean. You just add the numbers up, divide by the total count, you know the drill.
Right. Questions 9 and 22 test exactly this. Question 9 gives a short random data set, and question 22 gives the ages of 10 pregnant women at a clinic.
The math is just straightforward arithmetic.
Yeah, and the answers are 5 and 28, respectively. But what the exam is actually testing with the next few questions is, it's kind of a trap hidden inside the median.
Yes, the sorting trap.
Let's warn them about this.
Okay, so the median is the literal physical middle value of your data set. But if you just grab the middle number of an unsorted list, you fail the question immediately.
Question 4 is a perfect example. It asks you to find the median of this sample, 12, 26, 10, 29, 48.
Right, and if you look at the middle number exactly as it's written there, you'd pick 10.
And you'd be totally wrong.
Utterly wrong. You must sort the numbers from smallest to largest first. I can't stress this enough. It is the single most common, completely avoidable mistake on these exams.
So rewriting that list gives you 10, 12, 26, 29, 48.
And the number sitting dead center now is 26.
Which is the correct answer. Now, question 24 turns the dial up just slightly by giving you an even number of observations.
Right, 10 medical students' test scores.
Once you sort them, there obviously isn't one single middle number.
Because it's an even list, there are two numbers sharing the center spot, the 5th and 6th numbers.
Which happen to both be 6 in this specific data set.
So you just average those two together, meaning the median score is 6.
Simple enough once you remember to sort. And to finish out the trio, you have the mode.
Which is simply the most frequent value, the number that shows up the most often.
Question 18 lists 10 hemoglobin levels and asks for the mode. If you look at the list, only one number appears twice, 12.0.
Everything else appears only once. So 12.0 is your mode.
So we have the mean, the median, and the mode. But how do you know which one to actually trust?
That is the golden question, because out in the real world, data gets really messy.
And this is where the exam really tests your conceptual understanding of extreme values, the outliers.
I like to think about it like the classic billionaire in a bar scenario.
Oh, I love this analogy. Break it down for them.
Okay, so imagine you're in a room with 9 people, and they all make exactly $50,000 a year.
Okay.
The mean is $50,000. The median is $50,000. It's a perfect representation of the room. But then a billionaire walks through the door.
If you calculate the mean now, that billionaires' extreme wealth pulls the average up to, what, hundreds of millions of dollars?
Exactly. The mean is completely distorted. It paints a false picture, suggesting everyone in that bar is suddenly incredibly wealthy.
But if you calculate the median,
You sort the 10 incomes, and the guy making $50,000 is still sitting right there in the middle. The median is stubbornly resistant to outliers.
this is exactly why you constantly see public health officials report the median income or the median survival time for a disease.
Right, it protects the reality of the typical situation.
And your exam tests this directly. Question 21 asks, when the data set contains too many extreme values, the most representative average value is?
And the answer is median.
Question 27 provides actual clinical data to prove this point. You are looking at fasting blood sugar levels for 11 patients.
And most of them are floating in a normal or slightly elevated range, like 85 to 160.
But 2 patients arrive in critical condition with levels of 400 and 410.
Those are your billionaires walking into the bar.
Right. If you use the mean, the average shoots up to over 174.
Which represents literally nobody in that clinic. It's too high for the normal patients and far too low for the critical ones.
But if you sort the list, the median is 120.
And that is a highly accurate reflection of the typical patient sitting in your waiting room.
The median anchors you to the typical experience.
It does, but knowing the center is only half the battle.
Exactly. Because finding the middle feels like a false sense of security sometimes. Let's say the median resting heart rate in a clinical trial is 70 beats per minute.
Sounds perfectly healthy.
Right. But what if half the patients are crashing at 40 beats per minute and the other half are tachycardic at 100?
The middle is still 70, but literally everyone in the trial is incredibly sick.
Exactly. So how do we measure that chaos?
You measure the chaos using measures of dispersion.
Okay, let's unpack this.
These describe how spread out or how tightly clustered your data points are around the middle. We are talking about range, mean deviation, variance, standard deviation, and interquartile range.
First off, the exam wants to make sure you can separate the center from the spread.
Right. Question 6 asks which statistic does not belong: range, variance, mode, or standard deviation.
Well, mode measures the center, the others measure the spread, so mode is the odd one out.
And question 11 just flips it, asking which is not a measure of dispersion.
And the answer there is mean.
Now, the absolute simplest measure of dispersion is the range.
Question 10 and question 28 define range as the difference between the minimum value and the maximum value.
It just gives you the absolute outer boundaries of your data. So if your patient's heart rates go from 40 to 100, your range is 60.
Simple enough. Then there's question 17, which asks for the term that describes the, quote, average of the absolute deviations of the observations from the arithmetic mean.
That is a massive mouthful.
It really is. But the answer is conveniently right in the phrasing. It's the mean deviation.
But the exam gets a lot trickier with question 13.
Oh yeah, this one.
It asks, all the following are true for standard deviation except etiation. And the false statement you must identify is, the square of the standard deviation is called mean deviation.
Okay, this is where I actually want to push back because I look at standard deviation and variance and I keep getting them mixed up.
You were definitely not alone in that.
If variance is just standard deviation squared, why do we even need both? Honestly, it feels totally redundant.
I get that. It feels redundant until you look at the geometry of the math.
Okay, walk me through it.
Let's say you want to find the average distance. All your patients' heart rates are from the mean. Some are 30 beats above the mean, so that's a positive 30.
Right.
But some are 30 beats below, so that's a negative 30. If you just add those together to find an average, the positive and negative numbers cancel each other out, giving you exactly 0.
Oh, and the math thinks there is zero spread, which is absurd.
Exactly. So you square the distances because multiplying a negative by a negative makes it positive.
Ah, so squaring eliminates the negative signs entirely.
Precisely. It also heavily penalizes extreme outliers, making them mathematically obvious. That squared result is your variance.
Got it.
But here's the catch. Variance is no longer in your original units. It's in squared heartbeats, which makes absolutely no clinical sense.
Right. What is a squared heartbeat?
Exactly. So to get back to regular heartbeats, you take the square root of the variance, and that brings you back to the standard deviation.
Wow, that makes perfect sense. So variance is just the necessary mathematical stepping stone to get to the standard deviation.
You nailed it.
But wait. If standard deviation relies on calculating distances from the mean,
Yeah.
and we already established earlier that the mean gets totally ruined by extreme outliers, doesn't that mean standard deviation gets ruined by outliers too?
It absolutely does. If your data is heavily skewed by extreme values, you should not use the mean, and therefore you cannot rely on standard deviation.
Which perfectly tees up question 5. Which measure is not influenced by extreme values?
And the answer is the interquartile range, or the IQR.
Tell me about the IQR.
The IQR is basically the ultimate companion to the median. It's a measure of dispersion that completely ignores the chaotic outer edges of your data and only measures the spread of the reliable center.
That brings us to our final concepts: percentiles, quartiles, and comparing things that seem incomparable.
Right. To get to the IQR, you have to chop your data up into pieces. Percentiles slice your data into 100 equal parts. Quartiles slice it into 4 equal parts.
Question 3 asks what the first quartile, or Q1, is equivalent to.
Well, if you cut a data set into 4 chunks, that first cut sits at the 25% mark, so Q1 is the 25th percentile.
Makes sense. And question 12 asks what percentile matches the median.
The median is the absolute center, so it is the 50th percentile.
And the interquartile range is just the distance between Q1 and Q3, right?
Exactly, the 25th percentile up to the 75th percentile.
Which immediately answers question 20. Which of the following is true about interquartile range? The answer is that it covers the middle 50% of observations.
Let's apply this to a clinical scenario from the exam, like question 16.
Let's do it.
A physician observes 100 patients with COPD. The median lung volume is 2.0 liters, Q1 is 1.5 liters, and Q3 is 3.0 liters.
Okay.
The exam asks how many patients fall between 1.5 and 3.0 liters.
Well, 1.5 is Q1 and 3.0 is Q3. The space between them is the IQR.
Right.
And we just established that the IQR contains exactly the middle 50% of the people. Since there are 100 COPD patients in total, 50% of them is just 50 patients. So 50 is the answer.
Notice how the median and the IQR operate on the exact same philosophy.
How so?
They both focus purely on the stable, central bulk of the data, completely ignoring the wild extremes on either end. Because they share this philosophy, they are essentially statistical soulmates.
I love that phrase, statistical soulmates, which is tested in question 26. What is the appropriate measure of dispersion to report when median is reported as the measure of central tendency?
And the answer is always interquartile range. If you report one, you report the other.
Amazing. Now, there is one final concept we need to master today.
Right. Sometimes in health research, you need to compare the spread of entirely different biological metrics.
Let's say I want to compare the variation of blood pressure in a population, which is measured in millimeters of mercury, with the variation of cholesterol, which is measured in milligrams per deciliter.
Okay.
I can't just put their standard deviations side by side, right? The units are totally different.
No, you can't.
It feels like comparing a 5-inch variation in the height of skyscrapers against a 5-inch variation in the size of a parachute. Like 5 inches means absolutely nothing until you know the scale of the object you're actually measuring.
That is a brilliant way to frame it. To compare those variations, you really need a tool that strips away the units, the millimeters, the deciliters, the inches, and just gives you a pure relative percentage.
And that tool is the coefficient of variation, or the CV.
Exactly. Question 23 tests the definition. It asks, which of the following is a relative measure of dispersion when comparing variables which are measured in different units?
The answer is the coefficient of variation.
And then question 14 asks you to actually calculate it.
How do we do that?
The formula is simple. Take the standard deviation, divide it by the mean, and multiply by 100 to convert it to a percentage. You are literally calculating what percentage of the mean the standard deviation represents.
Okay, let's look at the numbers for question 14. You have 100 participants. The mean blood sugar level is 110. The standard deviation is 11. What is the CV?
So you take the ST of 11, divide it by the mean of 110, which gives you 0.1, multiply by 100, and your coefficient of variation is 10%.
Wow, just 10%.
Yep. And that 10% is your great equalizer.
Because it drops the units.
Exactly. If you calculated the CV for blood pressure in that same population, and it came out to, say, 5%, you could confidently state that blood sugar varies twice as much as blood pressure.
Because the completely different units no longer matter. You're only comparing the relative percentages.
Precisely.
That is incredibly powerful. And with that, we have systematically deconstructed all the concepts hidden within your Lecture 10 MCQs.
You really are armed with the actual conceptual logic to walk into this exam and dominate it.
You aren't just memorizing definitions anymore. You know exactly why age is continuous and not nominal.
You know why the variance has to be squared to eliminate negative distances.
And you know why the coefficient of variation is literally the only way to compare skyscrapers to parachutes.
You've moved past merely reading the data. You now understand the structural integrity of the statistics supporting it.
But before we let you go, I want you to take this knowledge out of the exam room and apply it to the real world.
Oh, this is important.
Think about how corporate PR teams, politicians, or even news headlines choose to feed data to you every single day.
Yeah, it's everywhere.
When a headline loudly claims that a new proposed policy will result in a mean tax cut of thousands of dollars for everyday citizens, but they conspicuously refuse to report the median tax cut, what are they actually hiding?
Who are the billionaires walking into that bar, right? Pulling the mean drastically upward, while the typical citizen in the middle sees absolutely no change at all.
Exactly. Once you truly understand how variables are chosen and how dispersion can be manipulated to tell a very specific story, you will never look at a statistic at face value again.
You really start spotting statistical sleight of hand everywhere.
That perfectly clean, objective data we tend to assume exists in health research. You realize it's heavily dependent on the human choices made by the researcher.
Look closely at the data they choose to highlight. Look even closer at the data they choose to hide, and you'll find the actual truth. Good luck on the Lecture 10 exam. You are going to crush it.